So we had run about Trump problem. And then there we show that show the relationship between the number of edges and the distance of certain subgraph. And we define this extremal number of G. External number of F. And then what we show is that if you have a n vertex graph where the extremal number is bigger, then the G contains F as subgraph. Okay, then what we can consider is that quantitative version of this theorem. So this says that if you have a number of graph, n vertex graph, whose number of edges is above the threshold, then you guarantee there is one copy of F. But we can ask how many copies? Of course, one obvious answer, it's easy to show that this many copies exist. Why? If you have this, then you find one copy and you delete one edge from here, and that copy is destroyed. And then this gets decreased by 1. And then you compare it still above, you find another copy, and then you destroy one edge, and so on. Then you get this many copies. But can we do better? That's the question. And what's the type bound? So just like the Turan theorem, the obvious graph to consider first is the clique, and especially the smallest non-trivial clique, which is triangle. So there is this theorem by Moon and Moser. That says that if you graph G with n vertices and m edges at least m over 3n times 4m minus n squared triangle. So this is theorem we want to prove. And what's this number? For example, if m is bigger than n squared over 4, then you have a triangle. Let's say n is even number to not consider this floor function. What happens if it's 1 bigger? Then this becomes 3n over n squared over 4 plus 1 times 1, which gives us that at least this many triangles are there. Instead of just one copy which comes from the Turan theorem, you have linearly many copies of triangles. And in general, if this one is bigger, then you would get what? The big number of triangles. If this one is, say, quarter plus epsilon n squared, excuse me, that you plug it in and you get the cubic number of triangles. And yeah, which is quite natural because the triangle, the incomplete graph, you have cubic number of triangles. So in dense graph, it's quite natural to have a cubic number of triangles, n to the some constant of n to the 3. So we want to prove this theorem. For that, let's define terminology. Let's say case of R, small case of R of G, be the number of KR, increase of side R in G. Okay, so before proving this Moon Moser theorem, so this is a kind of quantitative version, counting version of the what? Counting version of Turan theorem. And we can also consider counting version of Ramsey theorem. So for example, if we, in terms of this, what we know, the Ramsey number 3 is 6, means that if you consider for any 6 vertex graph, let's say n vertex graph with n bigger than or equal to 6, the number of triangles in G and the number of triangles in G complement is positive. So that's roughly what Ramsey's theorem says. Right? So in two-cornering or complete graph, red graph is G and then blue graph is its complement, then this is what it is. Then what's counting version? Then instead of just saying positive, we can ask how many, how small this can be. So that's natural question. So for given n, which is index 6, we know this is positive, but how small can it be in terms of n? So for, test this, in order to test it, we can consider some example. And one of the example is that you consider a random graph. Meaning that for each pair, you flip a coin, and then if it's head, you add an edge. If it's tail, you don't add an edge. So independently and random. So for n vertices, for each pair, you add an edge or not independently and random with probability half. Then, it's not difficult to actually check that with high probability, this is what? 1/8 times 0/1 plus 0/1 to the cube. No, not cube. And choose 3. So no matter how you choose 3 vertices, the probability that they form a triangle is 1/8. And then again you add it in its complement. So this is 1/4 times plus 0/1 times n cube. Somewhat surprisingly, we can show that this is asymptotically minimum possible. So in order to, if we answer this, then the answer is this, up to this zero function. Okay, we will first prove bounds on this, and then we will use it to derive this Moon Moser theorem. That's our goal. So somehow this counting version of Ramsey theorem is useful to answer the counting version of the Turan theorem. In this instance, if graph G has n vertices and m edges, then the number of triangles in G plus the number of triangles in its complement is n choose 3 minus half times summation of degree times n minus 1 minus degree. And if you rewrite it, then using handshake lemma, this is equal to this expression. So this equality is easy to check. This is n minus 2 minus p plus 1. Then this part, with handshake lemma, you get it, and the remaining one, you get this. So how do we do it? Basic idea is that, let's say you have a G, you have two colors. So red is G, and then blue is G complement. Then consider all possible triangles. There is essentially 3 cases. 4 cases. So there are these 4 types of triangle. Red one, blue one, 2 red edges, 1 blue, 1 red, and then 2 blue. And what we want to do is we want to count these 2 types while not counting this. So what we do is we give weights on the pair of incident edges. So I will show you. So we consider 2 coloring of the edges in AN and assume G is the graph with edges of 1 color, let's say red edges. But for 2 incident edges, we give weight 2 if they have the same color, and -1 if not. Then what? If you consider this pair, what? 2, 2, 2. So you get the weight 6 here and weight 6 here. On the other hand, here, this give you weight 2. This give you weight -1. This give you weight -1. So this and this weight 0. So the reason why we chose 2 and -1 is to make this have weight 0 and then make this have same weight. Then by adding weights, you can essentially count the number of these triangles, and then while not counting this, because 0 doesn't count and positive number counts. That's the reason why we give these weights. Then a vertex triple that induces a monochromatic triangle now contributes 6 to the total weight. While other triple contribute 0. So the summation of all weights of the incident edges is what? 6 times K3G plus K3G complement. But what's the total weight? For each vertex, we compute the weights of the edges they are incident at this vertex P. Then what do you get? You give 2 to each pairs of red vertices, which is degree of P, which is the degree of the first red graph, which is 2, plus 2 times -1 n minus 1 minus PB, which is the degree of blue one, which is 2. And then for any pair of red and blue one, you get -1. So you get this expression. But what do we know? We know that x choose 2 plus y choose 2 is same as x choose 2 minus y times x minus y. So using this, apply this, then this is summation of 2 times n minus 1 choose 2 minus 3 times degree times n minus 1 minus degree. You have this. And you sum over all b, and then divide by 6, then what you get? This is what? 6 times, so n choose 3 minus half times degree, half times the summation of degree, and 1 minus 1 degree. So you divide by 6, and you get exactly this formula. Okay, that gives us this answer. One thing we get from this lemma is that this value only depends on the degrees of the vertex. We don't care how G and G complement looks like. As long as we know its degree, then we get this. Okay. So from this, we can answer the counting version of the Ramsey theorem by optimizing this, how small this can be, which is Goodman's bound on n vertex graph and its complement together have at least n times n minus 1 times n minus 5 over 24 triangles, and it is sharp if when n is 1 mod 4. So how do you know? We take this equality. Then when does this get minimized? This can minimize if each of these terms is as large as possible. And then that happens where these two terms are as equal as possible. The sum is same, so if you have two numbers summing up to 10, and the multiplication is maximized when both are 5. This one is bigger than 1 times 9. So this gets maximized when they are as even as possible. So we can see that the minimization of the star, let's say this star, the star happens when degree of B is n minus over 2 for all vertex. Okay, so what? In that case, we have what? N choose 3 minus n half times n minus 1 square over 4, which is exactly this if you compute. Okay, and in order this to be the degree, what? We need the n to be odd, and it's had to be even. So if there are odd number of vertices, you don't have an odd regular graph with odd number of vertices. So that's from the handshake lemma. The only possibility is that n is odd in order this to be integer, and then this has to be even. So that means that the equality can only hold when n is 1 mod 4. In such a case, as long as there exists n minus 1 over 2 regular graph, then equality can be achieved. And then you just, finding one such regular graph is not difficult. So I will not do that, but you can easily check that there exists such a graph. For example, one easy way is that the the one is you take k vertices, k vertices, k vertices. Yeah, so and that's and one vertex here, and then it's complete, and all complete bipartite, and then it's all adjacent to here. And this is one such a graph. Okay. Well, before proving Moon Moser theorem, maybe we discuss a bit more about this. So what would be if R is bigger than 3? What is the minimum of the number of R clicks in G plus R clicks in G complement? Okay, before doing that, let me just mention that this number is what? 1/4 times n cube, roughly, with some lower term, which is roughly the number of triangles in G and G complement when G is the random graph. So for larger R, natural question is that again, a random graph is minimizer. It's a random graph minimizer. And it is conjecture that this is true. So he conjectured that yes to this question. So for R bigger than 3, again, the minimum answer is roughly the number of edges number of KRs in random graph, which is answers R times 2 to the minus R over 2. And you have to add a 2, so here 1. So this, but this was actually disproved. Thomason in 1989 disproved, and independently by Sidorenko. So this is not true. For K4, there are other graphs, non-random graphs, which had even smaller number of KR clicks in G and G complement, which is strictly smaller. So, the constant you multiply in front of entity R is strictly more than the constant you get from here. Okay, since then, there are more studies on the minimizer for this. Okay. Now we prove Moon Moser theorem. So we used this formula, and there it's written in terms of M, but you let M prime be the number of wedges in G complement, which is 1, which is n choose 2 minus M. And let's say D prime of G is the degree of G prime. Degree of G complement. Then what? This was that the K3G plus K3G complement n choose 3 minus M minus 2 M prime plus summation of D prime of G degree prime of B choose 2. And what do we know? one thing we know more is that if you take just complement, then the number of triangles there is at most what? This holds. Why? You take a vertex and then there are why? G complement edges, the blue one. And then you want to count the all blue triangle. What you do is here you count the pair of incident edges, pair of incident blue edges, pair of incident blue edges, pair of incident blue edges. You do that for all vertices. Then what happens is that the all monochromatic blue triangle is counted once, twice, 3 times. So they are counted all 3 times. Of course, it can be counted more in the sense that these are not supposed to be counted, but they counted by ones. But still, the inequality is okay. But this counts more than monochromatic blue triangle, but still this inequality holds. Okay, now what? We subtract the second one from first one, then what? We get K3 of G is at least n choose 3 minus n minus 2 over n prime and 2 over 3 summation of the degree prime choose 2. And what? It is n choose 3 minus n minus 2 times n choose 2 minus m plus 2 over 3. And then here you use the convexity of the function again. That's what? N times 2m prime over n choose 2. Because this degree sums up to m prime. Okay, so again, I mean, this is a bit more calculation. You replace this with the n choose 2 minus m, and then you compute this. I mean, yeah, this is computation that we will omit. Then you get this expression, proving Moon Moser theorem. Okay, so we proved that this is, I mean, what we have. But the natural case is whether this is best part. And you can check that if m is exactly the number of edges in this two-rank graph, then it is tight. It is best pattern. So roughly, I mean, how this shows, it shows that as m increase, the number of triangles in G, this is what? This is a linear function in, no, this is not linear. So this is quadratic function. So you get something like this graph. Okay, to be more precise, this is n choose 2, and this is n choose 3. So, and this is n squared over 4, this is 0, and then this is what? This is roughly the lower one. So, and this is tight for this, but the for general one, it's not tight. But we know that this is tight here. And what? You know that this is T2R, T2N, and then this is T3N. That's good. Okay, so this is the T3N. And T4, T5, T6, and so on. On these points, they are tight, but in general, it is not tight. And what would be the correct asymptotic. It's somewhat surprisingly, some function looks like this. So so these are convex, and then these are concave. So locally it's concave, but I mean globally it's like looks in this way. So it's some weird picture. So that's the minimum of the number of, triangles in terms of them. And this was verified by Razborov. He invented something called flag algebra. To find asymptotic answer for this K3G. And later, Ryer found the asymptotic answer for case of RG. And Stayden Hickelko found the exact answer for A3 of G when the number of edges is bounded away from edges 2. So difference between asymptotic answer and exact answer are like these. So this is asymptotic answer. So the leading coefficient is determined, but there are 3 error terms. But this is exact answer. So this is exactly we know every term. So for K3 we know the exact term as long as M is not too close to maximum possible. But for smaller one, only the leading coefficient is known. And then even with this leading coefficient, we have this weird looking function. Okay, so we talked about the relationship between number of copies of F, number of copies of a triangle and the number of edges in graph G. So we learned about G, Toran theorem, and then extremal number. And next time we will talk about, the random graph model, which we have used so far without explicitly, defining it. We technically, we defined it. So every time we consider random graph, we describe how we are going to generate it. But, next time we will talk about it a bit more. Yeah. Thank you for listening. I will see you next time.